Okay, so today's lesson looks at similar polygons. So that could be triangles, but it could be any kind of polygon. And dilation, so what happens when we dilate polygon. So at this starting point, you're going to use patty paper, but since you haven't used patty paper before, I'm just going to kind of show you what it means to use patty paper to compare the angles. So it says in the picture below, a triangle ABC, so this one, is similar to triangle DEF. So that little squiggly mark right there, it tells you right here, that means similar to. So these two triangles are similar to each other, which we're about to kind of figure out what that means to be similar. We talked about it a little bit when we did scale factor and area and volume ratios, but we're going to dive into it deeper here. So when we're using patty paper to compare the angles in triangle ABC to the angles in triangle DEF, you're going to use your patty paper and you're just going to I'm going to start, let's say, with angle A. So I can draw on my patty paper over angle A to kind of draw what it looks like. And then I can move it down here. I could compare it to angle D. I could compare it to angle E. So we're just looking like what do we notice about the three angles. So I want you to use your patty paper and go through that part of it. So this first thing that's telling you to do. After you write down what you notice about the angles, I want you to compare the ratios of the corresponding sides. Talk with your group about what you think corresponding sides mean, how we identify which ones are corresponding, etc. So, hopefully what you notice when you use your patty paper, I did one for A, B, and C, I just marked which one was which, is that you notice that angle A is the same or congruent to angle D. And then when we look at B, angle B is congruent to angle E. And then we look at angle C, mine was a little crooked, but angle C is congruent to angle F. So hopefully when you wrote down what you noticed, you wrote down those things or wrote down that there was three sets of congruent angles or something along those lines. Remember this symbol, the equal sign with the squiggly, means congruent to. So angle A is congruent to angle D, angle B is congruent to angle E, and angle C is congruent to angle F. So on the second question, when it's asking about corresponding sides, what I want you to notice is that the angles that were in the same location of this order of letters up here, so A was the first letter for this triangle, and then we said it's similar to triangle DEF, D was the first letter. Well, those were the two angles that were congruent. So when we're saying similarity statements, which is what we call this thing right here is a similarity statement, they go in order of the things that they correspond to or that they're similar to. So when we're talking about corresponding sides, side AB would be congruent, or not congruent, would correspond to side DE because those are the first two letters. So we're looking at this side together and this side together. So when it says compare the ratios, let's write the ratio of AB to DE. I'm going to go ahead and label where these ratios are coming from. So if AB and DE go together, then we have BC and EF that go together. So we have BC over EF, which is 12 over 8. And then last, we would have AC over FD or DF, whichever way you want to say it. AC over DF, which is 9 over 6. When you look at all these ratios, so we have 6 over 4, 12 over 8, 9 over 6. If you were to put that fraction into your calculator, they are all going to simplify down to the same fraction or the same decimal. All of these are equal to 3 over 2. That is the ratio of all the sides. So down here, what we're noticing in similar figures is the angles that correspond together. What we wrote on the first part was they're congruent. So A was congruent to D, B was congruent to E, C was congruent to F. And then corresponding side links. So when we looked at corresponding side links, for example, A, B, and D, E, they're not congruent because they're not the same. This one's 6, this one's 4. But when we compare the ratio of them between all the corresponding sides, they have the same ratio. So we call that corresponding side links are proportional. These two things are going to be really important when we talk about similar polygons. The angles have to be congruent, the side links have to be proportional. Otherwise, they're not two similar polygons. So, since proportions are going to be so important with similar figures, we're just going to review really quick how to solve proportions. We've done it a little bit when we did scale factor ratios and all of that. But remember, if we have a fraction here, this over this equals this over this, we can solve it by cross multiplying. There are other ways that you can solve besides cross multiplying. You can get a common denominator. We can see that 2 times 2 gives us 4, so we can multiply x plus 3 times 2 to give us, set it equal to this. There's lots of different ways, but typically I'm going to cross multiply when I do it on the key or when I do it in class. So we have 2 times 3 minus x equals 4 times x plus 3. So the two things that we circle, we set them equal to each other when we multiply. Now we distribute, so we have 6 minus 2x. And on this side we have equal to 4x plus 12. Move our x's to the same side. And then our constants or our numbers to the same side. I'm going to draw an arrow up here. That leaves us with, oh, I totally did that wrong. My apologies. I should have subtracted 4x, subtract 4x. So on this left side we get negative 6x. And then on the right side we have equal to 12 minus 6, so positive 6. We divide by negative 6. X equals 6 divided by negative 6, we get negative 1. If you're not sure, you can plug x back into the fractions and where the x is in the fractions, and it should come out to a true statement. So 3 minus a negative 1 gives us 3 plus 1, which is 4 over 4. 4 divided by 4 is 1. Plug negative 1 in here. Negative 1 plus 3, positive 2. 2 divided by 2 is 1, so we have 1 equals 1, and we're good. Okay, number 2 is something a little new. You may have seen it before, but we just need to talk about what it means to write a ratio of A to B. When I say the ratio of something to something else, that means A to B, A goes on top, B goes on bottom. This is the ratio of A to B. So we're going to solve this proportion the same exact way we just did. We're going to cross multiply. But eventually we're looking to get it in this form. So we have 3 times A plus 4B equals 4 times A minus B. Let me zoom in a little bit so you can see that better. Now we have 3A plus 12B when we distribute equals 4A minus 4B. We have A's and B's going on in both of these, so we have to move our A's and our B's together. So now we need to get our A's on the same side and our B's on the same side. I'm going to add 4B here and here. Subtract 3A here and here. There they cancel. And here they cancel. On this side we're left with 16B equals 4A minus 3A, we get 1A. So we have 16B equals A. You might be tempted to say the ratio of A to B is 16 to 1 or 16. But remember, we're wanting A to B, so we want A over B. If we can rearrange this to have A over B on one side, well, we want to divide by B. That's what we're looking for. But I can't just divide by B on this side and then pretend it's fine here. So I also have to divide by B there. My B's cancel. Now I'm just left with 16 equals A over B. So you always need to rearrange it so that it looks like A over B if we're looking of the ratio of A to B. So I would take either 16 over 1 or just 16. Okay. So now let's apply it to similar polygons. So it's telling us quadrilateral ABCD, so this inside small one is similar to the little squiggly line JKLM. So if these are similar in this way, it's telling us the corresponding sides AB and JK. So we have AB and JK. Those two are corresponding. BC and KL. So this one right here and this one right here. What do you notice between these two? Well, we multiply BC by 2 to get LK. We multiply 4 by 2 to get 8. So this figure is 2 times bigger than this inside one. So that means that 28 has to be 2 times bigger than whatever AB is. So we can do 2 times 2x plus 2 is going to give us that bigger shape. So we multiply our small side by 2 to get the bigger one, because we know this one is 2 times bigger according to this ratio right here. So now we distribute 4x plus 4 equals 28. Subtract the 4, we get 4x equals 24. And then last, divide by 4, we get x equals 6. Perfect. So flip to that next page. At the top, I want you to pause this video, practice this one on your own. Set up a proportion using this sentence right here, and then solve for x. Okay, when you set up this proportion, we had AB over BC was what they gave us, or AB to BC is 3 to 4. So when I set those sides over each other, AB was 45, BC was 4x was 20. We know that those are equal to the proportion 3 over 4, so I can set it up like this and cross multiply. So we have 45 times 4, that gives us 180. 4x plus 20 times 3 gives us 12x plus 60. When we distribute, move 60 around, we have 120 equals 12x. Divide by 12, you end up with x equals 10. I'm going to leave 5 for you to practice, and I will post the answer in a second, so if you need to pause the video a second to work on it, it should take you no longer than 2 minutes, I would say. Checking your answer for this one, you should have got the ratio of A to B as 2 to 1. I set my proportion up as A minus B over A plus B equals 3 over 9. So this should be your starting point. Then remember, we're moving things around to get A over B, because that's the ratio of A to B. This is going to be important. It will come up on tests and progress grades. If you need to go back and look at the key for this one that's posted online and look at the work more in depth, you can do that. But let's look at dilations down at the bottom. Let me zoom out really quick. So, at the bottom of this page, it says, in the figure shown, triangle XYZ, so this one right here is the blank of ABC. So, when we're looking at this, we're going to dilate triangle ABC to create XYZ. So XYZ is our new figure. So we call that, and we've heard this word before when we talked about translation, it's the image, it's the new one. The one that we started with, or did the original dilation to, is the pre-image. So pre means before, it's what we started with. In this case, the center of dilation, look what all the lines are pointing back to. It was O, or our origin in